Good afternoon. Anybody out there? Good afternoon. Okay, thank you very much. Let's get the blood into the brain. The last time we talked about a new state function, the entropy, and we did discuss the entropy of the universe is constantly increasing. So entropy is not conserved. Energy is conserved, okay? At the beginning, before the Big Bang, all the energy was in one point, and then the Big Bang happened, and ever since then, the energy, the total amount of energy hasn't changed, okay? But the entropy is constantly increasing, constantly, okay? So we're heading, and this is not a very bleak picture actually, we're heading for total chaos, all right? So fortunately it doesn't go that quickly, so we are going to be all right, but eventually the universe will head for total chaos. And with this you say, but the energy is conserved, so we could be able to still do work. No, the energy is distributed completely in the universe, and there is no order anymore, so we can't do any useful work. We can't get from a disordered system to a more ordered system, or vice versa. So there is no way that there can be any more work done, so there is no useful energy. Of course, the universe will have a temperature, it will have energy, but it is not useful energy anymore. So with this very encouraging outlook into the future, I would like to tell you that the change of the entropy of the universe, and we looked a lot at systems, is the change of the entropy of the system plus the change of the entropy on the surrounding. And the reason why we did this is we wanted to be able to predict if a reaction is spontaneous. So does that reaction happen spontaneously? And in order to happen spontaneously, the change of entropy of the universe has to be larger than zero, and we have cases where it is equal to zero. Then a system is in equilibrium, and we'll talk about this a little bit today. And there is no way that the change of the entropy of the universe is smaller than zero. This is not possible because of the reasons that I just explained to you. So we have said that the entropy is also a measure for disorder. So if you have the entropy of a system, that system will take the most statistically distributed, the statistically most likely microstate, okay? The number of microstates. And so with this you have, for example, if you look at ice, at liquid and a vapor of water. So you have different forms of entropy. And I'm asking you now, which transition involves the greatest increase in entropy? If I go from the solid to the liquid, from the liquid to the gas, or from the gas to the solid? Why don't you think about this and give me your answer? Please. So if you go from ice to liquid to gas, which one has the highest entropy? In the system. That's the motion of the gas. Okay. Yes, this is correct. So of course, you know that the solid, the ice is rather ordered. So there are crystals and they are on lattice, in the lattice, and they are on lattice positions. They are rather ordered, and so this will have the lowest entropy compared to the liquid. Liquids are pretty much ordered, but not as much ordered as than solids. And the most disordered are gases. So this has to be most possible microstates for gases. And I have shown you this in the last lecture, and I have tried to explain this to you in the last lecture with gases. So this is, I have depicted this here, the solid, rather ordered, so the entropies are small. Here the entropies become larger, and they become relatively very large for the gas. And with this, the answer was the gas. Now, what would be a system that has an absolute entropy of 0? What would that be? That would be a crystal, an absolute perfect crystal, but there are no perfect crystals essentially. An absolute perfect crystal, but if you have a temperature, so they are still having vibrations, the atoms, okay? So you have to stop the vibrations. How can you stop the vibrations at the lattice positions? How can you stop that? You have to go to absolute 0, exactly. And so there is no entropy of absolute 0, because we are unable to reach the absolute 0 temperature, okay? So this would be a perfect crystal at 0 temperature, would have the entropy of 0. Now let's look at another order-disorder transition. This would be the vaporization of a liquid at the boiling point, at the temperature of the boiling point. So this is easily to be understood. You have your liquid, it's relatively ordered, and then it goes to the gas state. It's very disordered, okay? And so you have definitely an increase in entropy. And so the entropy we have defined that the change in entropy in the standard reaction is the change of the reversible heat, the reversible heat, the exchange of the reversible heat at that temperature. That's the boiling temperature. So if you go from a liquid to a solid, you have to put in energy, okay? You have to transfer the molecules from the liquid phase into the gas phase. How you call that energy? Anybody heard about that? That's the energy of vaporization, okay? That's the enthalpy of vaporization. And with this we can say the change of entropy of such a system when we go from liquid to gas is the delta H of the vaporization, that's the vaporization enthalpy, divided by the boiling point. Now, if you plot this delta H over the boiling point for all kinds of different liquids, you will get actually a straight line, and that straight line, so this you plot H against T, so what will be the slope then here? What will be the slope? Say again? Yes? Yes, S, exactly. All right? And that slope will be, this is your S here, and that will be for many, many liquids, it will be about 90 joules. Remember now we have delta S is in joules, not kilojoules. Don't make a mistake when you do your calculations, okay? The delta H is in kilojoules, and delta S is in joules, so this is a big stumbling block here. It's 90 joules per Kelvin per mole for many, many liquids, and this makes sense because you go from that state of liquid to the state of gas. That's all there is. The liquids are essentially the same. They have a different boiling point, of course, but when they are at the boiling point, uses about the same energy, it's the same entropy change. They go from this liquid state to that gas state. But there's one exception, at least one exception. Which liquid is that? Water. Of course, water is always an exception. And water is a more ordered liquid because it has this, H2O has had these hydrogen bondings. which make it a little bit more ordered, not as disordered as other liquids. So that means that if you go from that liquid to the gaseous state, you have a larger entropy change than for the other liquids. And that's in fact what it is. The delta S, so this would be water, is the vaporization enthalpy is 40 kilojoules per mole. And so that would be then, it gives you delta S of the vaporization is about 110 joules per Kelvin per mole. As always, water behaves differently. Yeah? So there's a larger energy change of the transition between the liquid to the gas. So now I'm going to go and talk a little bit more, not a little bit, substantially much more, about a new state function. And we will derive that state function. And I hope you bear with me. So let's stay with water. We know if we are, you remember we did that experiment where we had the triple point of carbon dioxide. There was one temperature and one pressure where we could have the liquid and the solid and the gas at the same time. They were coexisting. All right? This is this one pressure. So the universe didn't care if the molecule was a liquid, a solid, or a gas. So that was in equilibrium. That means the change of entropy was equal to zero. Okay? That was equal to zero. Now we can do this for water. For example, there's a triple point for water. It's much more difficult to reach. There is a point where all the three phases are in perfect equilibrium. But if we look at a two-phase equilibrium, we have two-phase equilibria in water. One is, now let's do that. We do the liquid goes to the gas, all right? The liquid goes to the gas. That is the boiling of water. So the liquid goes to the gas, and if we get in equilibrium, the universe really doesn't care if it's gas or liquid, all right? And this would be at the boiling point of water. There's a perfect equilibrium between the gas and the liquid. So this would be at the boiling point, that would be 100 degrees Celsius or 212 Fahrenheit or 373.15 Kelvin. So we have the liquid go now to make it into the gas, into the vapor. So what will happen to the entropy? The entropy will increase. Isn't that right? Okay. Because we're going from the liquid to the gas. The entropy of the system, the delta S of the system, is larger than zero. So, but in order to make it boil, we have to put in energy. Okay? So what happens to the system? I take out energy to the surrounding. I'm sorry. I take out energy out of the surrounding. Will there be energy flowing into the system? Yes. So that would be positive or negative, the sign? Positive, okay. So that, delta H of the surrounding will be flowing into the system, all right? So there is this point, and what happens if the heat flows from the surroundings into the system? What happens to the surroundings? Does it get more ordered or less ordered? No, it gets more ordered or less ordered. If heat flows out, it gets more ordered, okay? It gets more ordered, all right? So what you have to say is there is essentially an enthalpic term, this is the enthalpy, and entropic term. And at that temperature, it is in perfect balance. And with this, you have equilibrium. The delta S equals zero. So that happens at the boiling point. What would be another point of equilibrium in the aqueous system, the water system? That would be the freezing point. So we go from a liquid to a solid. So that means to go from a liquid to a solid, we have to give enthalpy into the surrounding. It has to lower the temperature, heat has to flow into the surrounding, okay? All right? So that would be this here. And what happens to the entropy of the system? The entropy of the system, we're going from a liquid to a solid. What happens to the entropy? It gets smaller than 0, okay? It decreases. That would be this. And so at this point, this is 0 degrees Celsius, or 273.15 Kelvin, or 200, what's 0 in 0 is 32 degrees Fahrenheit. There you have that perfect balance between the enthalpic term and the entropic term, okay? And this is when you have equilibrium. Now, let's track the universe, the entropy of the universe. Good luck with that. Let's track the entropy of the universe. So you have the system is water. It goes from the liquid into the gas. Now, what can we say? The entropy of the universe has to be larger or equals larger than 0, equals to 0. It's the enthalpy change of the surroundings plus the enthalpy change of the system. Now, wouldn't it be incredible if we would have an experiment where two lab partners, one will determine the enthalpy, the entropy change, the entropy of the system, and the other one will determine the entropy of the surrounding, okay? Which one would you like to be? System. You say system, system. I seen it, system. I'm going to do it. And the other guy said, you do the surrounding, you do the universe. And with this, of course, this guy is going to be there for, this person going to be there forever, yeah? Because there's no way that you can do that. So what we want to do, the entropy change of the surrounding, let's find a way to express this in terms of the system. So what we do, we go from liquid to gas, and I have explained to you the heat of vaporization. That's the heat of vaporization. So, is there a skunk in here? Yeah? Smells like a skunk is in here. That would be something. Always some excitement. So let's come back. We want to express the entropy change of the surrounding in terms of an entropy change of the system. So we know that the entropy change of the system is that going from liquid to gas is delta H vaporization divided by the boiling temperature, okay? So, but we know that heat has to flow in to the system. So that heat has to come from the surrounding. We can then say, the entropy of the surrounding must be the opposite sign than the entropy change, which I take the system here. This is the heat of the vaporization divided by the boiling temperature. I just put the negative sign in there, and with this I have it explained. All right? So now I have explained the entropy change of the surrounding in terms of the system. So now we have this point here, the entropy change of the system. This is we go from liquid to gas, all right? This would be probably a positive number. And with this we have the entropy change of the universe, okay? So we have expressed this now as system and this now as system. That makes it a whole lot easier to calculate these things because we don't have to look directly at the surroundings. We can use the system as such. And so what is this here? Now let's multiply this with minus T. I want to get rid of this here. So this is delta H, vaporization, minus T times delta S is, what is that? Delta H system minus T times delta H system is minus T times delta S universe. Isn't that? Okay. And this, since the delta S of the universe has to be larger than 0, this has to be smaller than 0. Okay? All right? It can be 0 for an equilibrium. Now, temperature is a state function, isn't it? And we determined that the entropy is a state function. So we have two state functions, and we just give it a new name and have a new state function. And that new state function is the free energy, the Gibbs free energy. Delta G is the Gibbs free energy. We just leisurely say the free energy. All right? And this has to be smaller than 0 for any reaction to occur spontaneously. So all we do, we look at the delta H, the delta S of any reaction, and calculate the delta G, and then I can tell you this reaction will go spontaneous, or this reaction will be in equilibrium if delta G is 0, or this reaction will not occur. It's not spontaneous, not going to happen. So with this, we have now a very, very important equation. That's the Gibbs free energy. And now we got it all together. First we thought it was maybe the enthalpy change that drives the reaction, because when we went uphill, we had these big bangs here, okay, the release of energy. Then we said, no, it's the entropy change. The entropy has to increase in order for the reaction to happen. Also true, okay? But it's the combination of them. And it's the combination of the enthalpy of the system minus the temperature of the system divided times the entropy of the system gives you the free energy of your reaction. So delta, the G is H minus TS. So if I differentiate this and I have this as at constant temperature, and this is very important, if you give delta G values, you have to give the temperature, all right? There is really no standard state. There's a standard reaction. This is 1 molar reactants and products, or 1 atmosphere if they are gas, but the temperature you have to specify. So we can give this nut here. That means at standard state. This would be at standard state, this would be at standard state, and this would be also at standard state. But make sure that you specify the temperature. So what can happen? If delta H can be negative, okay, we roll down enthalpy hill, or it can be positive, we roll up enthalpy hill. These are possibilities. The other possibility is that the entropy, the S here, can increase. We roll up entropy hill, or we roll down entropy hill. But what never can happen, or what can never happen, is that the free energy becomes positive. Okay? It has to be negative. There is no up a free energy hill. So for spontaneous processes, delta G has to be smaller than 0. That's this here. And with this, like with any good old state function, you can look these values up. You can calculate it. So the delta G naught at standard state or standard reaction is the sum of the enthalpy of the free energies of formation. So this is the free energy change. It's the free energy of formation of the product, the sum, minus the sum of the free energy change of the reactants. And if this is negative, then the reaction goes. If it is 0, you're in equilibrium. If it's larger than 0, no go. Okay? All right, that's simple. Now let's listen and let's look at this and let's play a little bit. We have delta G and H minus T times delta S. So I want to show you the interplay between delta H, delta S, and the temperature. So we can have, for example, an endothermic reaction. An endothermic reaction, this would be positive. Endothermic would be positive. We plot this here. This is 0. This is positive delta S. This is negative delta S. This is positive delta H. This is negative delta H. We can plot this. So delta H is positive. That would be in this branch here. Now, the next possibility is delta S is smaller than 0. Delta S is smaller than 0, so that would be here. So this is this quadrant. Delta S is smaller than 0. That means this, if this is negative here, this becomes positive, and this is positive. You think that this will happen at all, this reaction? No. At no temperature, this will happen. Now, the other possibility we have an exothermic reaction. Exothermic is always good because delta H is negative. Delta H is negative. This would be somewhere here, okay? And then, let's see, the other thing is we have delta S is larger than 0. Delta H is larger than 0. So this is negative, and this remains negative. okay, would happen at what temperatures? Every temperature, isn't that right? At all temperatures. So it happens. Now, the next possibility would be we have delta H is endothermic. That means that would be negative. And delta H is endothermic. That is negative, would be that branch we are talking about here. And delta S would be smaller than 0. This would be this here. So what would happen? So delta H is negative, and this becomes, what would that be? Delta S is negative. This becomes positive. So what would that happen only at low temperatures or high temperatures, or what do you think? High temperatures? You sure about that? Okay, it's at low temperatures, all right? Of course it's at low temperatures, because otherwise this becomes too big here, all right? And it will overtake that term. Now there's the final possibility. We have delta H larger than 0, so that's endothermic, that's positive. And delta S is positive. So at what temperatures will that happen? That this becomes negative. Delta H and is positive, this is positive. So what temperature would that be? Now give me your answer. At high temperature, okay? That would be at high temperature. So there's this interplay between the entropy, the entropic term, the enthalpy, the enthalpic term, and the entropy, the entropic term, okay? Are you with me? Yes. You are? All three of you? Okay, all right. So it's not, yes, sir. Because otherwise the entropy will not, the reaction will not be spontaneous. Okay, I derived that for you. Okay, all right. So I can derive it again, but not today. So let's see, Henry, if you can answer that together with all your other colleagues. The reaction shown is spontaneous. So this is spontaneous reaction. This nitrous oxide, this reaction happens a lot in Los Angeles, okay? This is brown air, okay? and you have nitrous oxide, and this is a gas, and you have 2 moles, and then you make 1 mole of N2O4. Obviously, this is dimerizes here. So, and this is a spontaneous reaction. So this is what you need to look at. This is spontaneous. Delta G is negative, okay? Delta H for this reaction is what? So what is delta S? That's the first thing. And delta H for this reaction is smaller than 0, equal to 0, or larger than 0. Think about it. Nothing to calculate, just to think. So the first thing is you look at the entropy. What happens to the entropy? If I do like this, I do for this one like this, and for the other one like this. Okay? That's a private joke here. They're making fun of me when I do like this with the molecules, okay? But I get my point across. And it's great. You can make as much fun as you like, as long as you get it. Actually, they're not making fun. They just find it comical. So what is delta S, okay? So what is delta S? With delta S, you have the answer. What's the answer? No. Does the entropy increase or decrease here? Okay. So that must be a negative term then if the entropy decreases. But it is spontaneous. Oh, I'm sorry. Yes! Excellent! Of course. So I gave you the answer, essentially. So this has NO2. This has twice as many molecules than this one. So this is more more disordered than this one. This is more ordered. So the entropy has decreased. So the delta S is negative. If the delta is negative, this becomes positive, this term. In order for it to be spontaneous, it has to be delta G smaller than 0. How can delta G be smaller than 0? So with this, delta H has to be smaller than 0. Okay? It has to be exothermic, and there's your reaction delta G is delta H minus T times delta S smaller than 0. This is spontaneous. And with this one, we have delta S is smaller than 0, minus T times delta S is larger than 0. So in order for this to be negative, this has to be negative. Delta H is smaller than 0, and this is your answer. Great. Okay. We have now another plot. We have delta G naught, the free energy against the temperature for water, for liquid to gas. So in order to boil water, you have to increase the temperature, don't you? I gave you part of the answer already, all right? You have to increase the temperature. And so I want to know, if I plot delta G naught against T, would that the liquid to gas reaction, so the boiling of water, would that be the answer A, or the graph A, the graph B, or the graph C? So this is actually an equation here, okay? This is an equation, and if you know how to plot equations, this is Y, and this is mx, and this is B here, okay? And so why don't you think about this and give me, he speaks in miracles here. Think about this and give me your answer. Now we're going to come to the fun part soon. I don't see anybody with ties here today. Usually I see people with ties. Or the admiral. There must be elections maybe for boards and presidents of ASUC and so on. Huh? What was that? Joey Freeman, number 134. Is that you? Oh, you're a friend. Okay. All right. Good. Anybody else? Alex 10, number 69. Anybody else? Okay, great. So let's, please, I'm afraid that it gets out of hand, okay? Okay. All right, let's have a look here. I deserve that, okay? So, many of you say it's C, but quite a few are not sure about this. So this is a linear equation. This is delta G. This is y over x. So that would be x would be this here. What would be the slope then? And what would be the intercept? Okay? So why don't you think about this a little bit more? And what would be delta G? I help you a little bit more. What would be delta G at the boiling point? What would be delta G at the boiling point? 0. Okay, look for it. All right? Do I have to evacuate them or give them classes? No? Yes, I'm glad. Very nice. Very nice. Did you look for this point here? Okay. It could be also this one, though. Nevertheless, it couldn't be this one. Delta G has to be 0. This would be the boiling point. Or that could be the boiling point, but this is not the right slope, okay? So what we look at this here now, so delta G is H minus T times delta S. This has to be smaller than 0, okay? So delta S is larger than 0. That's the gas that is produced, okay? And with this, delta H has to be endothermic, so delta H has to be positive. Delta H would be the intercept here, for example. So you can say the negative slope is minus delta S here, okay? It's minus delta S. This is not. This is the slope here. And the intercept, what's the intercept? It has to be positive because where's the intercept? What is the intercept? What is it? Delta H, not, okay? This baby here, all right? So with this, this was the right answer. So that's a linear equation. Why are you laughing? Okay, so let's have a look. Let's have a look let's have a look at these tabulated values. So you see the delta H of formation is in kilojoules per mole. I have this for a lot of gases here and solids and some liquids here. Now, then you have delta S. No, there is no delta S. S is an absolute number, okay? Now look at the carbon solid, for example. Carbon solid, it's only 6 joule per Kelvin per mole. So it's a very ordered solid. If you look, for example, magnesium, the solids are pretty small. Magnesium solid here is 33, magnesium oxide is 29. So if you go then to the liquid here gets larger, 70 for the water, and then it goes into the gas phase, 189, the entropy change. Or for CO2, whereas do we have solid CO2? No, we don't. CO2 gas is 214, all right? So you see, be careful, this is in joules per Kelvin per mole. And this is always in kilojoules. Yeah? So make sure that you don't make this mistake. And this is the number that you can look up. Delta free enthalpy, free energy change, free energy change, okay? Free energy change of formation at standard reaction, and they are all tabulated, okay? Good. So let's have some fun. So we have potassium. We've thrown potassium in water. You remember that? We've thrown it in water. What happened there? It was fire, blue flames, huh? Blue flames and burning water. Very interesting, huh? So that was, obviously, there was an exothermic reaction. With this, delta H was exothermic reaction. Delta H was, there it is, okay? So how about, if you look at that reaction, how about the change in entropy? This is a liquid and a solid, and this is a liquid, and this becomes a gas. So the change in entropy is positive or negative? Positive, okay. Now the change of entropy is positive. What do you think that the change in free energy of reaction is? Negative, okay. It goes that way, all right. You throw potassium in water, it will happen, okay? So let's look at another one. We have H2O2 plus half a mole of oxygen gas gives, H2O, water, plus is a liquid, plus half a mole of oxygen gas gives you H2O, hydrogen peroxide, liquid. So actually this reaction is endothermic, I have to tell you that. All right, it's endothermic, that's positive. What do you think delta S is? Delta S is decreasing. Okay, and with this, what will happen with delta G? Yes, it doesn't go in this direction. Isn't it something? But if it doesn't go in this direction, why don't we do it in the opposite direction? Then it should go. All right? Let's do it in the opposite direction. Let me show you. We have here a beaker, and this beaker has hydrogen peroxide in there, and it doesn't go spontaneously. We need a catalyst, and this catalyst is what? Manganese dioxide. If we put manganese dioxide in there, we form water, vapor, and what else? And oxygen gas. Yes? Okay, let's do that then. Look at that, the water here. That oxygen. And it's very warm. It's hot water and oxygen. Beautiful, okay? Thank you, Karen. So it went the opposite direction. Now let's look at another one. We have here aluminum bromide. That's a solid. That forms aluminum, a solid, and a liquid bromine, okay? So again, I have to tell you, that's not exothermic. It's endothermic, all right? And what happens to delta S? We go from a solid to a liquid. What would that be? Delta S would be positive? Yes, it's right. And so with this, what would happen? Delta G would be what? It would work at low temperatures, wouldn't it? Would work at low temperatures, but essentially at room temperature, it is positive, it doesn't go. Why don't we do it? I don't know where she went. Why don't we do it this way? We take bromine liquid and put aluminum foil in there, and then we make aluminum bromide. This should be exothermic, should be exothermic, and it should be also delta G should be negative. And with this, we go in from liquid to solid, so that delta S should be decreasing. Are we ready? Bromine and aluminum. So the brown stuff is bromine, liquid. It's very volatile though. It forms also gas. And the silver one is aluminum foil. You can wrap your sandwich in. And there it goes. Flames. Oh. Like a magic brew you're making here. But you're not a witch, aren't you? Our chemistry witch, Karen. There she goes. She cannot laugh about that. There it is. Magic. Look at that. It only explodes every 10 times. It will go up eventually, but it does something. Shaky bakey. It's taken off in any second. Come on, yes. Let it sit for a second. Never listen to the professor. Come on. It reacted? Can you get some more aluminum foil? Yeah? We have time. We're not going to give up. Huh? Okay. So what happens is we put some more aluminum foil in and maybe a little more bromine. I hope that doesn't take off. But I want to see that. Usually it's a beautiful flame. And it forms this aluminum bromide, which is a solid. You can see the solid coming out on the sides here. And let's see if she has the aluminum foil. Give it a second. So why don't I explain the next one so far? We're going to do this also. We have solid magnesium and CO2. CO2 is solid carbon dioxide. Solid carbon dioxide. So we make magnesium oxide and carbon. So this goes into this direction. So this is an exothermic reaction with solid carbon dioxide. Can you imagine a reaction at very low temperature? And, oh, she's going to do it again. Very good. And so what can we say about the change of the entropy? This is all, this is all this. We can't say much. We need to calculate that. So it is negative, actually. So it decreases the entropy. And with this, this will be going only at low temperatures. At high temperatures, it will not go. But because CO2 is already very cold, it will help the reaction. So we do a chemical reaction at low temperature, essentially on dry ice. All right? So let's see if we can go with this one here. Yes, yes, yes. There it is. Beautiful, beautiful. Never ever give up. Never ever. Whatever you do, never give up. Okay? That's the most important thing in your whole life. Never ever give up. All right? And there it is. It didn't quite, but okay. Karen deserves a hand. All right? So now let's come to the last experiment. We're going to do the magnesium. And this is one of, next to the CO2 triple point, one of the most beautiful experiments, I think. You should stay around for that. So there is a dry ice block, and in the dry ice there's a hole. Karen made a little indenture, and she puts in some magnesium filing, and she puts the magnesium filing, we'll put them on fire then, light them up a little bit to get the reaction started. We're not fooling around here. That's the magnesium CO2 lamp. There it goes. Nope. Can you believe this? Can you believe this? Huh? Oh. Isn't that incredible? The yin and yang of chemistry, fire and ice. And delta G is negative. And I see you on Friday.